Welcome to this informative video exploring the idea of radionuclides and how half-life can be modeled as a decaying exponential function. But before we get into that, I would like to take you through some of the concepts that I think are relevant to understanding this topic. I will start by exploring the idea of radioisotopes. The incorporation of radioisotopes in the medical field has revolutionized diagnosis and treatment for many patients. Nuclear medicine has been used for its radioactive properties to help diagnose and treat a wide variety of diseases and disorders, as well as providing unique information about the human body and its health. Nuclear medicine has helped doctors and physicians diagnose diseases earlier to make treatment more effective, as well as get a broader understanding of the human anatomy. The benefits of these nuclear advancements come from exploiting the unique characteristics of radioisotopes, one of which is half-life. Half-life is the time it takes for half of the atoms in a radioisotope to decay. The importance of understanding half-life is that some radioisotopes used in nuclear medicine have shorter half-lives. This means they decay quicker and are suitable for diagnostic purposes. Others with longer half-lives take more time to decay, which makes them suitable for therapeutic purposes. Diagnostic techniques in nuclear medicine use radioactive traces which emit gamma rays from within the body. These traces are generally short-lived isotopes linked to chemical compounds which permit specific physiological processes to be scrutinized. They can be given by injection, inhalation, or orally. Gamma rays are a highly penetrating form of electromagnetic radiation that arise from the radioactive decay of atomic nuclei. This makes them particularly useful in creating 3D images of the internal human body without damaging cells. This is because gamma rays, on the other hand, have low ionization energy, which makes them harmless if exposed to in small doses. In PET scans, the gamma rays used for imaging are produced when a positron meets an electron inside the patient's body. An encounter that annihilates both electron and positron and produces two gamma rays traveling in opposite direction, which are picked up by the machine. Radionuclides may occur in nature or be manufactured in a laboratory. In medicine, they're used in imaging, tests, and in treatment. Most frequently, radionuclides are chemically bound to a stable molecule or compound chosen for its ability to localize in a specific organ system. The combination of the radionuclide bound to a molecule or compound is known as a radiopharmaceutical. The stable bond with molecules makes radionuclides more useful as traces for certain areas in the body. In this video, we will be looking at a specific radiopharmaceutical known as technetium. Technetium-99m is an isotope commonly used in a number of medical diagnostic imaging scans. Tc-99m is used as a radioactive tracer for nuclear medicine, which is a form of medical imaging that assesses how particular parts of our body are working or functioning. Technetium-99m is a short-lived form of technetium-99 that is used as a medical diagnostic tool. It has a short half-life of 6 hours and does not remain in the body or in the environment for too long. Tc-99m is used in medical therapy for the brain, bone, liver, spleen, kidney, and thyroid scanning, as well as for blood flow studies. Tc-99m is the radioisotope most widely used as a tracer for medical diagnosis. It can be readily detected in the body by medical equipment because it emits gamma rays, which are about the same wavelength as emitted by conventional X-ray diagnostic equipment. These unique characteristics make it the most commonly used medical radioisotope in the world. The advantages of technetium are that it examines the metabolic processes without significant harm to the patient due to the short half-life, allows rapid diagnosis. It also allows non-invasive diagnostic procedures on the heart, brain, kidneys, and thyroid that would not be otherwise possible. It can also be used in radiation treatment of cancers. There are different forms of technetium-99m, which means that it will travel to different organs in the body, thus allowing for specific diagnostics, and there are no side effects on the patient. Half-lives are a good example of an exponential function. We can use half-lives to model a decaying exponent. Before we get into that, it is important to understand what an exponential function is. In an exponential function, the independent variable, or x value, is the exponent, while the base is a constant. For example, y equals a to the power of x would be an exponential function. The formula for an exponential function is y equals ab to the power of x, where a and b are constants and x is the variable. For a binary relation to satisfy an exponential function, a and b must remain constant and b must be bigger than 0 and not equal 1. To make this definition coherent, I will show you an example. Suppose in one situation we had to graph the mass of bacteria in a culture over an hour in 10-minute intervals. The starting mass of the bacteria is 63 micrograms, and the growth rate is 1.5 times the previous interval. We can present this problem as m bracket t bracket equals a times b to the power of t, where a equals 63 and b equals 1.5. T would be the number of 10-minute periods after the starting of the observations. The reason t is a power in this equation is because after 10 minutes, the mass of bacteria is 63 times 1.5, and after 20 minutes, it is 63 times 1.5 times 1.5. Or we can simplify it to 63 times 1.5 to the power of 2, and etc. And if we insert this equation into Desmos, we can see how the results are plotted. So at 0 intervals, you can see that the line crosses the y-axis at 63. After one interval, it crosses at 94.5 because 63 times 1.5 is 94.5. And after two intervals, it crosses at 141.75 because 63 times 1.5 to the power of 2 is 141.75. In Desmos, you are able to convert a function into a table of results to make it easier to view the data. And we can see by looking at the 6th interval, which is about an hour, that the mass of the bacteria would be 717.61 micrograms to 2 decimal places. This is an example of an increasing exponential function. In this topic we are exploring today, we are observing a decaying exponent. This can be easily graphed using the same formula with different constants and variables in Desmos like so. We know that the number of atoms in 1 mole of technetium-99m is 99. So A would equal 99, and to show that the number of atoms halves after a certain period of time, A would equal a half. The little a would equal a half. X would be the number of intervals, and each interval would be 6 hours because that is the half-life of technetium-99m. Using the table of results, we can see that after 6 hours, the number of atoms in the radiopharmaceutical decays to 21.5. At 12 hours, it decays to 10.75. At 18, it is 5.375, and at 24, it is 2.6875. So using those results, we can say that the number of atoms remaining in technetium-99m after 24 hours is approximately 3 to 0 decimal places. To summarize this video, we have understood the various characteristics of radioisotopes and how we can exploit these for medical purposes, specifically surrounding technetium-99m. We have also understood how the half-lives of radioisotopes can be modeled as a decaying exponential function. I hope this video has helped in understanding some of these concepts and how exponential functions can be used in the real world. Y'all have a good day.